Industry is advancing, agriculture is developing, livestock is expanding. However, behind this progress, there is an invisible threat: ammonia. Ammonia gas, or NH3, is a toxic compound released from industrial waste, livestock manure, and agricultural fertilizers. Even at low concentrations, as little as 25 parts per million, ammonia can cause respiratory irritation and pose a health risk. Not only for humans, ammonia also damages air and water quality and contributes to environmental pollution. To address this, we need a fast, sensitive, and efficient ammonia gas monitoring system. Sensors based on semiconductor materials such as zinc oxide or ZNO are a promising solution. ZNO particles have high sensitivity to harmful gases, but still have the disadvantages of slow response time and low surface area. The solution, combining ZNO with activated carbon from biomass waste, such as coconut shell charcoal. Activated carbon has a large surface area, high porosity, and excellent gas adsorption capacity. This combination forms a heterojunction structure, which significantly improves the detection performance of ammonia gas. Let's go, we will see how to make it. So, to find out more about this ESP32-based ammonia gas sensor, let's take a look at a snippet of the manufacturing process. The process of making an ESP32-based ammonia gas sensor consists of several important stages, namely 1. Preparation of activated carbon from coconut shells. 2. Synthesis of ZNO nanoparticles. 3. Preparation of ZNO activated carbon nanocomposites. 4. Fabrication of interdigital electrodes. 5. ESP32 sensor assembly and integration. In the first process, namely the preparation of activated carbon, coconut shell charcoal is burned and ground finely, then chemically activated. Soak in 1 molar hydrochloric acid solution for 3 to 6 hours. Rinse until neutral with distilled water, filter with gauze, dry in an oven, then carbonize at a temperature of 500 to 600 degrees Celsius for 2 hours. The process continues with the synthesis of ZNO nanoparticles. In this process, a chemical reaction occurs, namely Zen 2 plus 2 OH minus arrow ZNOH2 ZNNO32 was dissolved in 100 milliliters of distilled water. NiOH solution was added dropwise while stirring. Avoid rapid addition. Addition of NiOH will form a white precipitate of ZNOH2. The solution was continuously stirred for approximately 30 minutes. The solution was then left overnight, or 6 to 12 hours. Then the precipitate was filtered and washed with water until neutral. Dry the precipitate in an oven at 60 to 80 degrees Celsius. Calcination of the dry powder in a furnace at 400 to 500 degrees Celsius for 2 hours, until a white ZNO powder was formed. The third procedure is the manufacture of zinc oxide activated carbon nanocomposites, which is carried out by inserting the synthesized ZNO particles and activated carbon into a mortar, slowly ground until homogeneous. Ethanol is added while continuously stirring the hot plate stirrer for 30 to 60 minutes at a temperature of plus or minus 60 degrees Celsius. Oven the mixture at a temperature of 80 to 100 degrees Celsius for 4 to 6 hours, or overnight until completely dry. The interdigital electrode fabrication process begins with designing a serpentine pattern using software, then printing and gluing it to a bare PCB. The paper is then removed with water, leaving only the ink to act as a protective shield for the copper. The PCB is then immersed in a solution of FeCl and water to dissolve the copper that is not covered by the ink. After the dissolution process, the electrodes are inspected to ensure all the paths are as designed and that none are broken. The The final procedure is the assembly of the sensor and integration of the ESP32 by dispersing 10 to 20 milligrams of ZNO carbon nanocomposite in 1 milliliter of ethanol. Assemble the sensor by connecting the electrode to a breadboard, connecting one pin to VCC 3.3 volts and one to a 100 kilo ohm resistor to GND, then taking the midpoint to the ESP32 ADC analog pin. You can see that this sensor has been successfully created and has been proven to be able to detect ammonia gas in the surrounding air by utilizing natural materials and B3 waste, which is harmful to the environment. This sensor is integrated with the ESP32, an energy-efficient microcontroller that allows this system to be portable, low power consumption, and easy to use for real-time monitoring. Imagine with just this small sensor, we can monitor air quality in industrial or livestock areas in real time and prevent the risk of air pollution from ammonia gas early on. This innovation not only answers the need for gas sensor technology, but also carries an environmental saving mission, reducing waste, utilizing local resources, realizing sustainable green engineering. Because clean air is the right of all living things, and innovation is the key.